I am Dr. Basir-Ahamed-Khan, Assistant Professor of Physics, Krishnath College. This is the lecture 2 of module 8. In my previous lecture 1 of module 8, I already discussed about the introduction of thermodynamics. Basically, I discussed in my previous lecture on zeroth law of thermodynamics and the concept of temperature and thermodynamic variable, extensive variable, intensive variable and state function, etc. Now today in lecture 2 I will discuss mainly 3 points. First point is the internal energy of thermodynamic system. Second one is the first law of thermodynamics, and the third one is thermodynamic processes. Now the first topic, internal energy. Internal energy basically is defined as the sum of total internal kinetic energy of all molecules, because since I consider thermodynamic system, basically if we consider a system of gas, then internal energy basically define the total internal kinetic energy of all molecules and potential energies of all molecules and this is the representation of internal energy of the system. That means internal energy, if I define the internal energy by capital U, then internal energy is the total kinetic energy of the molecule, total kinetic energy of molecules plus potential energy of all the molecules, potential energy of all molecules. This is the definition of internal energy. Now in practice it is not possible to measure the total internal energy of a system. In practice basically it is not possible to measure the total internal energy of a system in any given state. That means we cannot measure total internal energy in a given state. Only I can measure its value, only change of this value we can measure. That means the difference or the change of internal energy, this quantity I can measure. Suppose a system in an initial state 1, initial state 1 a system, I represent initial state as 1 and final state 2. That means a system and initial state 1 changes to a final state 2 by supplying heat capital Q to the system. That means initial state 1 changes to final state 2 by applying or by supplying the amount of heat capital Q to the system, and if capital W is the work done by the system during the change, then increase in internal energy of the system is given by increase in internal energy of the system is given by U2 minus U1 equal to, from the conservation of energy we can write Q minus W. This is equation 1. I repeat again this point. Now if a state of the system is changed from an initial state 1 to final state 2, initial state 1 to final state, initial state 1 to final state 2 by supplying Q amount of heat, and if capital W is the work done by the system during this change, then increase in internal energy U2 minus U1 equal to Q, from the principle of conservation of energy, U2 minus U1 equal to Q minus W, where U1 and U2 are respectively the internal energy of state 1 and state 2. So this is the, from the conservation principle, we can, conservation of energy, we can say that the change of internal energy U2 minus U1 equal to Q minus W. Now internal energy of real gas and ideal gas. Now I will discuss the internal energy of real gas and ideal gas. Internal energy of real gas or and ideal gas. Internal energy of real gas and ideal gas. The internal energy is of an ideal gas is only depend on temperature. Internal energy of ideal gas, that means internal energy of ideal gas depends only on temperature. Depends only on temperature. But internal energy of real gas depends on temperature and volume. Temperature and volume, or temperature and pressure. Now how can I explain this? Suppose for ideal gas, the internal energy for ideal gas, internal energy is only equal to the kinetic energy of its molecule. We already said that internal energy is the total kinetic energy of molecules plus potential energy of all molecules. Total kinetic energy of molecules plus potential energy of all molecules. This is the internal energy. This is the definition of internal energy. Here, when I calculate the internal energy, or I obtain the internal energy of ideal gas. In ideal gas, I said that the internal energy depends on temperature. How I can explain it? In ideal gas, the internal energy wholly is equal to the kinetic energy. That means internal energy is only equal to the kinetic energy of its molecule. So internal energy for ideal gas, internal energy, there is no potential energy. That means for ideal gas, internal energy means kinetic energy, kinetic energy of all molecules, kinetic energy of all molecules, kinetic energy of all molecules. So here there is no potential energy for ideal gas. Therefore, internal energy is equal to the kinetic energy of all molecules for ideal gas. Now we know that from the kinetic theory of gas, the kinetic energy of molecules is proportional to kT. Kinetic energy of molecules, kinetic energy of molecules of molecules proportional to is proportional to molecules is proportional to kT, where k is Boltzmann constant and T is temperature. So kinetic energy of molecules is proportional to kT, where k is Boltzmann constant, k is Boltzmann constant, and T is the temperature. T is the temperature. T is the temperature. Therefore, we can say that internal energy of ideal gas, therefore we can say that internal energy depends on temperature. That means internal energy is function of temperature only. This is the concept of internal energy is depends on the temperature. That means function of temperature only. Internal energy is a function of temperature only. Now for real gas. Now for real gas. We know that internal energy is kinetic energy of molecules plus real gas obeys van der Waals equation. Real gas obeys van der Waals equation. Real gas obeys van der Waals equation. Therefore, internal energy equal to kinetic energy plus potential energy. Kinetic energy plus potential energy. Kinetic energy is proportional to, this is proportional to temperature. This is proportional to temperature. This is proportional to temperature. And this is the force potential energy of molecules due to the mutual force of attraction. This force of attraction depends on intermolecular distance. Potential energy of molecules due to mutual force of attraction, and this is force of attraction. This force of attraction depends on intermolecular distance. I repeat these things. Potential energy of molecules due to their mutual force of attraction. This is the potential energy of molecules due to mutual force of attraction. And this force of attraction depends on temperature, depends on this force of attraction depends on intermolecular distance, and hence it is a function of volume. This is proportional to volume. This is proportional to volume, and this is proportional to temperature. This is proportional to volume. Therefore, we say that for real gas, the internal energy is a function of both. Internal energy is a function of both temperature and volume. Or other words, we can say internal energy is for real gas is a function of temperature and pressure. Therefore, in ideal gas, internal energy only depends on temperature. That means internal energy is a function of temperature only. And for real gas, internal energy is a function of temperature and volume, or temperature and pressure. Now, first law of thermodynamics. First law of thermodynamics. First law of thermodynamics. First law of thermodynamics. Thermodynamics. First law of thermodynamics. Thermodynamics. First law, the statement is that the amount of heat supplied to a closed system, the amount of heat supplied to a closed system is equal to sum of increase in the internal energy of the system and the external work done by the system. I repeat again, the amount of heat supplied, the statement, first law of thermodynamics states that the amount of heat supplied to a closed system is equal to sum of the increase in the internal energy of the system and the external work done by the system Suppose du be the change in internal energy of the system when dq amount of heat is added to it. Once again, let du amount of internal energy be change of a system when dq amount of heat is added to it, and dw amount of work is done. Amount of work is done by the system. Then first law of thermodynamics can be represented mathematically as du equal to dq minus dw. This is the change of internal energy of the system when dq amount of heat is added to the system. And during this change, if dw amount of work is done by the system, then from the conservation of energy we say that du equal to dq minus dw. This is the mathematical representation. dq equal to therefore dq equal to du plus dw, and this is the mathematical representation or differential form of first law of thermodynamics. This is first law, mathematical form of first law, mathematical form of first law of thermodynamics. This is also called differential form. This is also called differential form. This is also called differential form of first law of thermodynamics. Now, for an infinitesimal quasi-static process of hydrostatic system, the first law can be written as dq equal to du plus pdv. dq equal to, since dw for hydrostatic system, dw equal to pdv, since dw equal to pdv, then dq equal to du plus pdv for hydrostatic system. This is the first law of thermodynamics. Now, thermodynamic processes. Thermodynamic processes. A system is said to be undergo a thermodynamic process when the values of its thermodynamic variable or coordinates changes from one equilibrium state to other. Basically, a system is said to be undergo a thermodynamic process when the values of its thermodynamic variables or coordinates changes from one equilibrium state to other. That means the change of thermodynamic variables. In my previous lecture, I already told what is thermodynamic variable. In case of gaseous system, the thermodynamic variables are pressure, temperature, and for volume P, T and V. These are the thermodynamic variables. The change of, that means the thermodynamic process is undergo, means the values of thermodynamic variables changes from one to another. Now, first one is isothermal process. Isothermal process. In this process, a process where temperature is kept constant is called isothermal. Temperature in this process, the temperature should be constant. Then the process is called isothermal process. That means temperature is constant during this process. In this process, isothermal process means temperature is constant. Suppose this is a plot PV diagram. This is pressure P and temperature volume V. If I plot PV diagram of ideal gas for a particular temperature, then I will get this type of curve. This is, suppose this is V1 P1, V1 P1, this is V2 P2, this is V2 P2, this is V2 P2. This is isothermal process. Isothermal process. Isothermal process. Isothermal process. Now, isobaric process. This is isothermal process means T is constant. Second one, isobaric process. Isobaric process. During this process, pressure is constant. That means a process in which pressure is kept constant. A process in which pressure is constant. Pressure is constant. Pressure is constant, and this process is known as isobaric process. Suppose if I plot PV diagram, here temperature fixed. In this process, isothermal process, this is temperature fixed. Temperature fixed temperature. This curve for fixed temperature. The second one, this is PV diagram, P, this is V. Isobaric process means pressure is same, pressure is constant. That means we get a horizontal line with V axis. This is a horizontal line with V axis. This is isobaric process. Isobaric process. Next one is isochoric process. Isochoric process. A process in which volume is kept constant. A process in which volume is kept constant. A process in which volume is kept constant. Then the process is called isochoric process. Volume is kept constant. This is isochoric process. That means in this PV diagram we can write, this is V, this is pressure P, we get a vertical line. This is the isochoric process. That means In every point of this line we get the same volume. So this is isochoric 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 process. Now adiabatic process. Adiabatic process adiabatic process adiabatic process adiabatic process, a process in which there is no exchange of heat between the system and the surrounding. There is no exchange of heat. There is no exchange of heat between system and the surrounding. Between system and the surrounding. Between system and the surrounding. There is no exchange of heat between system and the surrounding, then the process then the process is then the process is called adiabatic process. Adiabatic process. Adiabatic process. Adiabatic process. Basically, adiabatic process happen very rapidly and isothermal process happen very slowly. Adiabatic process happens very abruptly, very fast. That means during this process there is no scope of exchange of heat. There is no scope of exchange of heat between system and the surrounding. Basically, there is no exchange of heat between system and the surrounding. In between them there is no exchange of heat. Then the process is called adiabatic process. That means if a process, during this process there is no exchange of heat between the system and the surrounding, then the process is called adiabatic process. Now quasi-static process. Quasi-static process. Quasi-static process. Quasi-static process. Quasi-static process. If during the process a system differs only infinitesimally from an equilibrium state, that means quasi-static process is a process which is very slowly such that the system departs only infinitesimally from an equilibrium state, and at every instant the system remains virtually in a state of equilibrium. I repeat again, that means a system during this process, a system changes into initial state to final state. This is initial state to final state. Initial state to final state, changes from initial state to final state. A system changes initial state to final state during this quasi-static process. I can say that in every step the system is virtually thermodynamic equilibrium. That means the system departs only infinitesimally from an equilibrium state. That means thermodynamic variables are changes very slowly, and this is during this process we can, in every step we can say the system is in thermodynamic equilibrium. In quasi-static process, the coordinates of the system, pressure, volume or temperature, vary physically indefinitely slowly, so that the system is found all the time in an equilibrium state. So that in every step, thus or all every time in the system is an equilibrium state. This type of process is called quasi-static process. That means quasi-static process occurs very slowly, occurs very slowly, very slowly, very slowly, and it remains virtually in a state of equilibrium. And during this process, and during this process, during this process, the system, during this process, the system remains virtually in a state of equilibrium, remains virtually in a state of equilibrium, state of equilibrium, equilibrium. This process is known as quasi-static process. This process is known as that means this process occurs very slowly, and during this process the system remains virtually in a state of equilibrium, and this process is called quasi-static process.